Click for Biology 216, explaining the importance of the surface area to volume ratio as a factor limiting the size of a cell. Here the command term is explain, and there's the definition. So we're looking for reasons, mechanisms and causes. So let's start off with a simple idea of a simple cell like this, and this cell is taking in oxygen by diffusion for respiration, and we can measure the surface area around the cell at 4 units, and the volume is 1. So we've got a ratio of 4:1. Now if we take the same cell and maintain the volume, same volume, but we increase the surface area by folding, we might get a shape that looks like this. So our volume is still 1, but we've increased the surface area for the absorption of oxygen. So we've got more surface area for absorption. So let's notionally increase this to 8 units. So the ratio is now 8:1. And so the surface area to volume ratio has increased. So for the same volume, but with a folded surface, we've got a larger surface area to volume ratio, and so we get more diffusion. The rate of diffusion would be greater. So by folding a surface, we can increase the rate of diffusion by increasing the surface area. A more numerical example of this would be to idealize the cell as a cube. So this is supposed to be a cube, and of course the side would be measured at 1 unit. So for instance, this would mean that the surface area would be 1 times 1 multiplied by the 6 surfaces, which is 6 units squared. And the volume would be 1 times 1 times 1, which would be 1 unit cubed. So the ratio here is 6:1. So let's try and take this back to the biological. So this unit cell can take in oxygen here and here, here, underneath of course, in at the side and in at the back. It has 6 surfaces to take in, for instance, oxygen. So let's make this cell bigger. Let's treble the size. So let's see if we can draw that. And let's draw in the original size of this cube here on top to illustrate the volume and surface area effects. So this is a bit rough, but I think you can see that what we've got is a cube where the surface area is now 3 times 3 times 6, so that's 9 times 6 equals 54 units squared, and the volume is 3 times 3 times 3, which is 27 units cubed, giving us a ratio of 54 to 27, which can be reduced to 27, which can be reduced to 2 to 1. So what does this mean? Well, if we examine the cubes, we can see that whilst this one has 6 exposed surfaces, the same volume here would only have 3 surfaces exposed to the exterior. This surface, this cube here, has only 2 surfaces. This one only has 1 surface exposed for absorbing oxygen, and of course right in the very center of this cube there's another cube which is completely unexposed, has other cube cells around it through which oxygen has to diffuse before it arrives at the central structure. So as the surface area to volume ratio decreases, the rate of diffusion and movement of substances now will also decrease. If we have a cell, there are certain advantages with that cell becoming larger. Some of those advantages are, for instance, as it becomes larger this way, it can become more competitive with other cells. But as we go this way, the surface area to volume ratio decreases. Now, the cell requires things like nutrients going in, oxygen going in, perhaps carbon dioxide coming out, and waste molecules coming out, and the rate at which we take in oxygen, nutrient, carbon dioxide, and excrete waste is dependent on this ratio. So the question is, how big can a cell get before the rate of exchange becomes too slow? And the answer is that for plant cells, they can get as big as 100 micrometers, and animal cells can get as big as 10 micrometers. Beyond this, plant cells, if they get bigger than this, the rate of uptake of oxygen is too slow because the ratio is too small.